Welcome everyone. In this video, we will solve a GATE 20 2007 question in which we have to find out the mode of operation estimation in a BJT. So this one is GATE 2007 question. So in this question, the given things are for the BJT circuit shown. So this one is the BJT circuit shown with beta value is very high, beta value is very large, and base emitter junction voltage is zero point 0.7 volt. Then we have to find the operation of the BJT, mode of operation. Either should be cutoff, saturation, active, and this is a reverse active mode. So first of all, in such question, first we have to just put the terminal name base in collector, arrow sign will be our emitter, and the given thing is plus or minus VBE is the given. Okay, so now what I have to do, so H, we know some basic concept regarding the BJT. If the base emitter junction, I am writing base emitter junction when forward bias, base emitter junction forward bias and base collector junction is in the forward bias. So this condition when both is in the forward bias base emitter junction. So one can write this as a VBE, okay, and this as a VBC. When both are forward bias, or we can say VBE is positive and VBC is also positive, okay, like 1.7, so 0.7 or 2 or 3, when both are positive, okay. I'm just once again writing VBC and VBE should be some positive positive number. So this is in the saturation region. This one is a very important condition, saturation region, or we can say saturation mode. The transistor will be acts as a saturation mode. So for more detail, you can go for the Bosted book, very fundamental book. Okay. One more property that I am going to write, when VBE is positive and VBC is negative. Okay, I am just writing base emitter junction positive and base collector junction negative. So it is in the linear region, or better to write active region. Better to write active region. This one is very important. That's why I am writing. After it, we will solve this question mathematically. Okay. Now last one we can say, when both base emitter junction is negative and base collector junction is also negative, so it should be in, sorry, it should be in cutoff mode. Cutoff mode. So these are the very important points, that when both are positive, it is in the saturation region. Okay, and when both are negative, it is in the cutoff region. And when base emitter junction is positive and base collector junction is negative, then it is in the active region. So this point we have to know, and this is the very fundamental, and it is coming from Boston book. I am writing from the Boston book, so it is very clearly mentioned the means conditions how to think. Okay, so now this condition is very useful. You can use in some other problem also. So now what we have to do in this question, the given thing in this question, the given thing as beta is very large. What it means? Beta is very large means IB value will be nearly zero because IC equals to beta times of IB, and IB we can write as IC by beta. Beta is very large, so that's why if beta is greater than or 100 or 200, okay, so this value will be very low. Okay, generally it is in the microampere range. Yes, so microampere range. So now we have to neglect when beta is very large, we have to neglect the base current. Okay, this thing is given, and the other thing is given the base emitter voltage. Everyone knows VBE is 0.7 volt. So this VBE is also given. The VBE value I am writing here. VBE is 0.7 volt. Okay, so VBE is our positive. So one thing we know, the VBE is our positive value. Okay, so VBE is our positive value clearly. Okay, now we can say VB value and VB value is 2 volt because it is connected here. So this voltage will be a 2 volt. So VB value will be 2 volt. So that's why VB value is 2 volt and VBE is zero point 0.7 volt. But we cannot know the value of VE, okay, and VC, okay. So what we have to find? We have to find base collector voltage, okay. VBC means if we find VB minus VC, then we have to find this value is either positive, negative, then we can decide. Okay, so that in this question we have to find VBC. Okay, so now it is given the value of VB is zero point 0.7 and IB is very large. So we can say this current is our collector current IC, and IB is 0. So one can write IE equals to IC because IB is 0. So as fundamental formula I equals to IB plus IC. So this IB will be 0 because beta is very high. Okay. So IE is nearly equals to IC. So this value will be IC. So this current will be also same as IC. Okay. This one is a very fundamental concept that beta is very large. We have to make IB equals to 0. So now if we apply Kirchhoff's voltage law in this loop, Kirchhoff's voltage law in this loop, so we can easily find the value of IC. So how we can find? So I am writing by applying Kirchhoff's voltage law KVL in loop 1. Okay, by applying Kirchhoff's voltage law in loop 1. So how we have to write the KVL equation? So I am starting from here, okay, from 2 volt. So I am writing 2 volt, okay, plus then minus VBE, minus VBE, minus VBE, minus IC. We are going in the current direction, so I am using this assumption minus IC into 1 kilo ohm, 1 into 10 to power 3 equals to 0. Very simple. 2 minus VB minus ICRE. Okay, this one is very simple. If we are saying this is a RE, we have to write, again I am writing 2V minus VBE minus ICRE, the same thing I have written here. Okay, both are same. Okay, now VBE value is already known to us, so we can write as 2 minus 0.7, and we can write this as a volt, IC into 10 to the power 3. Okay, so now we can write 2 minus 1 point, sorry, 0.7, this should be 1.3 volt, and IC into 10 to the power 3, or you can remove this volt. So IC can be simply our 1.3 by 10 to the power 3, means 1.3, better to write milliampere. IC will be milliampere. Okay, you can remove this volt, or you can put, not a big deal for this one. Okay, so IC value now known to us. Now if this IC value is known to us, now we have to find this value, plus minus, and this voltage is our collected to beta voltage. Now what I am using, what we have to do, we have to apply KVL in this loop. Okay, now by applying KVL in this loop, we can find the value of VC. So what we are doing, by applying KVL in loop 2, by applying KVL in loop 2. So what we have to write, again KVL. So I am just starting from here, from 10 volts. So directly we can write, okay, I am writing 10 minus, current direction is like that. So I am just using, I am just writing IC into 10 into 10 to the power 3. Okay, plus minus. So we have to write minus VC, simple KVL concept, minus then IC into 10 to the power 3 equals to 0. 10 volt minus 10 kilo ohm into IC minus VC, we are living from here, so minus VC minus IC RE. Okay, or once again I am writing this is a 10 minus ICRC minus VCE minus, we can write IC RE equals to 0, because this IC and IE are same due to beta is very large. Okay, so now we have to solve for VCE value. So if we put VC in the right hand side, we can write this as a 10 minus this one IC to 10 to the power 3 and IC 10 IC. Okay, so we can write it 11 IC into 10 to the power 3 minus 11 IC equals to VCE. Now we can find the value of VCE equals to 10 minus 11 into IC value is 1.3 milliampere, 10 to the minus 3 into 10 to the power 3. Now we have to solve this one. 10 minus 11 into 1.3. Basically we have to find the value of VB, VC, okay, and VE, because if we know the VE and VBC, we can easily say in which mode it will work. So that's why we are finding VBE is known to us, but we don't have VC. So that's why we are doing all this operation, we can say. Okay, so if we multiply 11 into 1.3, it should be 10 minus 14.3. Okay, So VCE value, we can easily say VCE value minus 4.3 volt. Okay, so I am just highlighting this one. VC is our known to us. Now VCE value is our known quantity. Okay, so now we can easily find the value of, okay, once again I write it. VCE is our minus 4.3 volt. So we can write this as a VC minus VE equals to minus 4.3 volt. Now VE is known to us. Okay, we can easily say how VBE equals to 0.7 volt. So this one is nothing but simply VB minus VE. Okay. Now 0.7 VB is our 2 volt. VB is our 2 volt. We clearly say this voltage is 2 volt. So VB is our 2 volt minus VE. So VE we can write as 2 minus 0.7. So it should be 1.3. Okay, 1.3 volt. Okay, again highlighting this one. This type of practice you have to do, and it is very simple. Okay, VE 1.3. If VE is 1.3 volts, so 1.3 minus 0, we can easily say, suppose this RE resistance, I am just making this, okay, I have to select pen, means for the, if this one is RE and this value is given, VE is our 1.3 volt, RE is 1 kilo ohm, and this one is grounded. So this IC we can easily say, sorry, IC, because IC equals to I is there. So we can say this should be VE. VE, higher potential minus lower potential 0 by 1. So it should be 1.3 milliampere. Okay, this way 10 to the power 3. So I see we have already 1.3, so we can easily identify we are going in the right direction. Okay, so we have to know this type of thing. So VE is 1.3. So here VC minus VE is 1.3 volt. So minus 4.3 I am writing. So VC value we can write minus 4.3 plus 1.3. So it should be our 3 volt with minus sign. So VC will be minus 3 volt. Now what we have to find? VBC. So VBC, VB minus VC, base to collector voltage. So VBC is our, VB is given 2 volt. Okay, VB is already 2 volt. Okay, you have to know the network concept. This potential will be 2 volt. So I am writing 2 volt minus VC. VC is minus 3 volt. So it should be 2 plus 3. So 5 volts. So what we observed, VBC value is our 5 volt and VBE value is 0.7 volt. Okay, and both are positive. So it is working in the saturation region. So this one is the fundamental way to think how to estimate the transistor operation using simple mathematics, using the concept of network. But we have to know this one, VBE and VBC value will be positive. So it is in the saturation region. When both are in the negative, both negative, VBE and VBC, it should be in cutoff, and VBE positive, VBC negative, it should be in the active region. So in this way we can easily say the correct option answer for this one is our saturation region. Okay, so this is all about this simple gate 2007 question. So thank you for watching this video.